the webinar. I'm really excited to start the webinars off for this year. And as Subhajit said, I just defended my PhD, and I am very excited to be done with the academic, years that I have spent with the PhD, with the master's, and with the undergrad. And I'm very excited to be joining the industry in this field very soon. I will share my presentation. So I don't have an introduction slide, and I'm really glad that Subhajit kind of went through the introduction beforehand. But just to start off, as Subhajit said, I did my bachelor's, my master's, and my PhD in the US, and I just defended just about 2 months ago, and I graduated officially in December. And all of my studies were in aerospace engineering, and I specialized in astrodynamics and satellite navigation in both my master's and my PhD. As Subhajit said, my research is focused in space situational awareness. And what I'll be talking about today is a very brief overview of what I did during my PhD, and then also a little bit of the technical snippets of what tools were used in this process as well. And since I think it's a good group, and I think we can do questions during the presentation as well, unless there are any objections to that. So if you have any questions, feel free to raise a hand, or Subhajit, is that okay? Or do you want to just take questions at the end?
It's up to you, whichever makes you more comfortable.
Okay, then questions during the presentation are also fine. If anything comes up, please feel free to bring it up. Okay, let's start with why it's important to study space situational awareness, which means just being aware of the objects around you and objects that are occupying the same space, so that we can avoid collisions and we can maintain safety and sustainability in space as well. So why has this issue become more important in the recent years? In near-Earth space especially, we have over 27,000 catalogued objects that are greater than 10 centimeters in diameter, and they are ever increasing. We have launches almost every day at this point, with so many constellations, small sats, and just general rocket bodies, debris, and everything else that has been increasing the count of these resident space objects. And this is an increasing issue even in Cislunar space, which is the space between the Earth and the Moon, because we are starting to see a lot of growth in these Cislunar missions as well. There's a really large number of debris that comes from collisions, which is one of the big reasons we want to avoid them. We want to avoid these number of objects increasing even further. There are a few ways that currently allow monitoring of these objects, and one of the big ones is the US Space Surveillance Network, the SSN, which monitors and informs on close encounters between two of these or multiple one of these objects. And it provides this information to many of the commercial as well as government organizations to ensure that objects don't collide in space. Now, the sensors we have to observe these objects are very limited in number because there's a hardware limitation. This means that we can only see many of these objects at large time intervals. So we'll notice the object at one point, we will take the reading again, but that would be maybe some hours, maybe some days after the initial observation. So that always causes issues in space situation awareness, because you don't always know where the object is, because it's not always monitored. This brings us to why it's important, why the work that I do is important. And a big part of that is monitoring of these resident space objects. Each of these objects, when they're monitored by either a ground telescope or a radar or in-space observation techniques, what happens is we get two things about this object. The first one is the state, about where the satellite is. And the second one is its uncertainty. What this means is that, let's say, we can say that this object is in this position and with this velocity with a 98% confidence. What does the 98% confidence mean? That it could be anywhere in this 98% ellipse that is drawn around the satellite. It's very important to note the accuracy of these observations and have this percentage of uncertainty associated with the state, because we can rarely ever be 100% sure of where an object is. And that means that when we propagate this forward, we have to ensure, let's say this is the general trajectory for a satellite in space. We have to ensure to take into account, there was this animation that I missed, but this initial location of the satellite can be propagated further with simple dynamics, and we can know that the satellite that has started at this initial state 1 will move in this orbit to state 2. It's really important to account for this initial uncertainty, because this also translates to where the object can be expected to be in the future. The nonlinearity in the dynamics in space leads to this simple ellipse that we see from observation resources getting warped at this final time of propagation. Why is this important? Because this shape that we see in the end, let me turn on the annotate. This shape that we see at the end, that is crescent shaped, it's important because the satellite could be anywhere in this shape. If we had maintained the elliptical shape around this, which is a simple 2D ellipse, it would miss these tail ends of the crescent shape that appear in these uncertainties. It's a little intricate explanation, but because of the dynamics in space, we see this behavior appear. So how is this important? Again, it's important because it tells us where this object can be at a future time, and that leads to many, many applications in space situational awareness. Just a second. So what's the technique that has been traditionally and historically used in this industry? It's the Monte Carlo analysis, which is a simple numerical analysis. What we do is we take millions of points in this initial ellipse that I defined, which is essentially the uncertainty of where the object could be at this initial time. And we propagate each of these millions of points further to get this final crescent-shaped uncertainty at a future time. This is very, very accurate if we can include millions of points in this analysis, but there's a drawback to this, which is that it becomes really computationally expensive the more points we have in this initial uncertainty. So you can imagine each of these trajectories, each of these points is propagated over time using the system dynamics, which takes a lot of time, and that makes this method very expensive to use. This brings us to why this work is important. Even though the Monte Carlo can provide us with really high accuracy of where the object could be in a future time, it is also very computationally expensive. This is why we look for alternate methods to this that are analytical and semi-analytical, which means that there is a direct relationship between the final state and an initial state, meaning that we don't need numerical propagation for all of these points. We can do a direct analytical mapping of this initial state to a final state instead. Now, it's important to account for accuracy in this as well, so that we can get close to Monte Carlo numerical accuracy. And it's important to keep the computational expense low. This is primarily what I did research on, building toolkits, mathematical toolkits that can propagate this initial information about a satellite to a final time. A really big application of this work is to avoid collisions. And how can we do that? Is by performing conjunction analysis. If we have two of these objects at initial time, and we propagate each of them, even if they don't intersect directly, even if their uncertainties overlap at this final time, there can be a collision between these objects. Why is this important again? Because we need to know where these objects can be at a future time to avoid and predict these collisions. This makes this a very important study. I will go through a very brief method outline and then define some of the components before showing you some of the results out of this method. We have these initial distributions of the two objects, which are the two uncertainty ellipsoids. What we want in the end is to analyze these crescent-shaped uncertainties at a final time. We implement a couple of mathematical tools in this. The first one is the Gaussian mixture model, which is a really simplistic tool, really, where we split up this initial full uncertainty into really small uncertainties or really small ellipsoids. And we do this because it's easier to propagate each of these individual ellipses forward and to keep them ellipse-shaped for a long time. We propagate each of these with a mathematical tool called STT, which allows us direct mapping from this initial uncertainty to a final uncertainty. And what we get is that each of these small ellipses get propagated, but they give us this big crescent shape that we were hoping for at this final time. And these components can then be compared to perform the final conjunction analysis or collision, probability of collision calculations. I will skip this for the most part, but all this is showing you is how we model the dynamics in the near-Earth space, which is essentially taking the average of the orbital element and then adding the short period variations at a final time. I will go through this really briefly. So what does this look like in action? We have this full trajectory that includes the full dynamics. We take the mean and we propagate the mean to the final time, and we add a short period offset at the end to include accuracy in our results. I will show you a brief example of what the results of this look like, and this is again going a bit technical, but these are really exciting results where with the dynamical system, we can propagate just the mean of the element and add small variations at the end to accurately capture our orbital trajectory over time. You can see that in the end, when we add these small variations, we can match our full propagation. This saves us a lot of time in propagation in near-Earth applications. Let's skip this. So a quick description of how this initial uncertainty ellipsoid gets split up into these smaller ellipses is again a very simple mathematical tool called the Gaussian mixture model, where we split this big ellipse into these small ellipses, where the big ellipse is just a sum of these small ones in a mathematical weighted sum. How do we map these forward? Is by component propagation. Each of these means gets propagated. Each of these ellipses gets propagated. And we get our final mapped crescent shape. This initial shape, it leads to this final shape by the individual small component propagation. And we get our final nonlinear transformation. I'm skipping over some math, but if anyone has specific questions on that later on, I can answer that. I'm going to go briefly over this as well. It's a very similar method to what I showed a few slides ago, but now this is analytical, where we're mapping these initial components into the final components using this mean propagation method. Now, there are two types of conjunctions that we studied, and I'll share brief results on each of these. The first one is short-term encounter, where two satellites cross each other's path very briefly, and it can also be termed as an instantaneous encounter. The other one is a long-term encounter, which we see primarily in GPS orbits, where two satellites remain close to each other for a longer amount of time. We studied both of these test cases in our PhD study. The first thing that I'm presenting, this is a very quick description of how we calculate probability of collisions. In the numerical methods, what we do is the method that I described in the beginning, where we take millions of points for each of the objects, propagate them forward. We get these crescent-shaped uncertainties, and we compare them to get our probability of collision. The number of points that do end up within a small hard body radius of the combined objects versus the total number of points in the analysis gives you a probability of collision of the two objects. It's a very simple formula that we implement. And we add confidence bounds to ensure that our analytical results fall within this true numerical analysis. For the choice of dynamics, I briefly described the Near-Earth system, but I can go in depth on that later. But that one is just a simplified dynamical system where we use average propagation. The Cislunar domain is a simple CR3BP, a circular restricted three-body problem dynamics that we use. This might still be too technical, but I will go along with it. Then these are the two toolkits that we developed. The left one is the Near-Earth method that we developed, and the right one is the Cislunar method. And I will briefly describe the methods of each of them. We have this initial distribution. We convert it into a GMM split distribution where we have these small components. We propagate each of these forward using state transition tensors. We get this final crescent shape, which is the final uncertainty of where the object could be at a final time. We convert them to Cartesian frame, and we get this final conjunction comparison. It's a very similar method in Cislunar, where we keep everything in Cartesian all along, whereas in Near-Earth, we had some coordinate transformations. Same conjunction analysis methods implemented in both Near-Earth and Cislunar space. And the last part of this is the probability of collision that we use with the analytical methods. And that one is a simple 2D analysis formula that helps us compare each of these objects, each of these small components of the distribution versus the other to give us an all-in-all probability of collision. That was, I know, a little bit technical and maybe a little long, but now I'll share just a couple of really quick results that are the really exciting part of this research. Starting with the Near-Earth regime, we analyzed a collision between two satellites, and the time of closest approach was 1.5 days after the initial observation. They are in fairly low Earth orbits, around 8,000 and 9,000 kilometers from the center of the Earth. On the top right, you can see how this uncertainty at a final time looks with numerical data. You can see that it gets spread out into this crescent shape for both of these objects. The real exciting part were the results, where we can see that the diamond-shaped results from our analytical method match the numerical results of our probability of collision within our required relative errors. And the speed difference between the two methods was really dramatic, where in the full dynamics Monte Carlo, it took us 5 days to run the probability of collision analysis. Whereas with our method that we implemented for analytical results, it took about 4 minutes. So we're going from 5 days of analysis to 4 minutes of analysis using the technique that we developed with these toolkits. That's about 1,700 times faster in the results, and really exciting to see the successful results in the Near-Earth cases. This is specifically for short duration conjunctions, so very instantaneous passes. But we saw the same results in long duration conjunctions as well. And I'll share a quick result for the Cislunar regime as well, which is including the lunar dynamics and closer to the moon. In this, we also developed an example where we had 7 days of propagation time. We can see the complex trajectories that these objects will follow, their uncertainties. And similarly, the results ended up within our Monte Carlo numerical simulation results. And again, this was a dramatic improvement in time, where we went from 5 days to about 500 seconds in our final analysis. This is about 400,000 times faster. Or actually, we went from 5 days to 1 second with the one component result. So it's a very dramatic improvement in time here as well. That's kind of all I had for the technical presentation, but on the left, the 2 QR codes and the 2 links are to these toolkits that are available online to test out, play with the code however you want. And on the top right is my LinkedIn, and the bottom one is my email. So if you have any questions afterwards, you can contact me there as well. I wanted to keep the technical parts a bit brief, and I don't know if anyone here has the expertise or the interest in this area, but I can take questions on the technical side or on the personal side for anyone that is interested in following a similar academic path. So that's all I had, and I can answer any questions now.
Thank you so much, Yashika, for that amazing and very interesting presentation. And congratulations on the work that you have done. It's absolutely fantastic. So this is to all our audience. If you have any questions, you can feel free to put it down in the chat, or you can also raise your hand using the raise hand option, and maybe we can have a direct one-on-one question. So please feel free to ask anything. As Yashika said, it's not necessarily has to be something technical or about the work that she just presented. If you have any questions regarding career paths or how to follow this particular field, you can also ask that question, because Yashika has seen it all. So she will surely guide you with her experience. All right, Yashika. So we have a question from one of our participants. So he asks, his name is Damien. So Damien asks, how do you know? Uh, just a second, I cannot see the question properly. So he says, how do you know what math knowledge you need to use? That's his question.
Hi, Damien. I think that's a really good question. PhDs are usually quite complex in a way that you have to do a little bit of your own research, but you also get a little bit of your own guidance from your advisor that you work with. I think if you're asking specifically for PhD research, then I would say it takes a lot of browsing through books and papers and just a lot of reading in general to find out what mathematical tools can be implemented in specific research. And if you're talking about the general field, it is kind of everything. It's a little bit of everything that is included in astrodynamics and in space research. So it's kind of a mix. I hope that answers the question, but I can also go more specific if you need.
Thank you so much, Yashika. So anyone, if you have a question, please feel free to raise your hand, or you can also put your question down in the chat. All right, so Rachel asks, what software or languages are used in this field to make the models?
That's a great question, Rachel. So when we are doing the research, specifically PhD, masters, in aerospace engineering in general, a lot of the work is done in MATLAB. Most of the research is done in MATLAB because it's a very easy to learn and very convenient language to use. But I have also implemented similar methods in the industry during internships in C, C++. I use Java and Python. And there's another language that's coming up now, which is called Julia, which is gaining a lot of traction in astrodynamics as well. So there's a lot of software and languages that are used, and there's anywhere you start is a good place. I don't know if you're already have experimented with them or not, but Python and MATLAB are really good ones to start with.
Great. Thank you so much, Yashika, for that really great answer, and also introducing the new tool, Julia. So Dia asks, what skill sets do we need to build a career in SSA?
Yeah, it's a really good question, Dia. I think I don't think there's one answer for this, because SSA, you can approach it from many directions, right? From policy standpoint, from engineering standpoint. If you're specifically interested in research, I think having a good mathematical and a good code base is a really good way to start, because as you can see, like a lot of this work includes software development, and a lot of it includes mathematical and physics tools as well. So that's a good place to start with, and having undergrads or masters in similar fields like physics, astrophysics, astrodynamics, aerospace in general is really good, because it really supports the work that you will get into with SSA. And again, SSA can be approached from a lot of directions because SSA policy is becoming really important recently. And from the engineering standpoint, there's a lot of different ways to approach it as well. So it kind of depends on what area you want to really go into and how it can be applicable in SSA. But space situational awareness in general is it's becoming a really, really big field of research because of just how many objects we have in space right now and how fast they're increasing. So really depends on the field you are starting off with, but there's a variety of things that are really important, and math, maybe some policy background, maybe some engineering background, physics background are really good to start off with in SSA.
Awesome. Thank you so much, Yashika, once again. So guys, if you have more questions, please feel free to put them in the chat section. I'm sure we have some time to answer your questions. So feel free to put them. Or if you want to ask Yashika directly, you can also raise your hand and then I will call upon you to unmute yourself and ask Yashika directly.
Yeah, I see Damien's question, which was what was the nominal TCA? That is the nominal time of closest approach. That means from the time that you have an observation for an object, how much time after that do you expect the two objects that are in possibility of conjunction will be closest to each other? So it's the time that two objects that are possibly going to collide are going to be closest to each other. And in the examples that I presented, in the Near-Earth case, we look at closer or faster turnaround time. So we have around day and a half, 3 days of time of closest approach. But in cislunar testing, we look at longer propagation times. For instance, in our examples, we used anywhere from 7 days to 30 days of propagation. To clarify, this means that we don't have any data on these objects that are in space for 7 days, 14 days, or 30 days. And we are simply propagating this information forward using the mathematical tools that we have developed. I hope that clarifies, Damien.
Thank you so much, Yashika. And there's also one more question from Rachel, as you can see in the chat. Are the toolkits developed by you currently used in the industry or will they be used in the future? And secondly, how did you verify the accuracy of the results?
Both really good questions, Rachel. So firstly, the toolkits that I have developed are not currently in use because they were just developed and the papers on them have just been published in the last few months or maybe even the last couple of years. Currently, the industry uses a lot of numerical methods, which is what we were trying to improve the times of, right? So we saw that the numerical methods in some of the results took 5 days and 6 days to run, whereas the methods we are developing are taking seconds or minutes to run. So this is kind of something that is going to be useful in the next couple of years and is going to be seen in the industry in the next couple of years. And it's something that I've actually implemented at one of the internships that I had a couple years ago as well. So parts of it, so making their analysis more analytical is something that I have done for employers that I have done internships for. So it's really exciting to see these new methods that are so fast come up in the industry now. And how did I verify the accuracy of results? I think I shared this briefly in the slides, but the way that the industry calculates the real probability of collision or close to real is using numerical methods, which are the ones in my results that take 5 days to calculate the probability of collision. So that is the result that we use as truth. And we compare our method against that to ensure that our method is generating accurate results. And I can reshare the screen briefly, but you can see in this, I'll just share it quickly. I think the Neart-Earth results are more exciting, but in this you can see the solid blue line in these result plots are the Monte Carlo or the numerical results, which are taking us 5 days. They are considered really accurate measures of probability of collision. So the blue line that you see here is the accurate result using the numerical methods that are taking 5 days in the table at the bottom. The diamonds are from our results that we are generating using our methods. You can see that in the right relative error plot that they are falling within a very low relative error between the numerical versus the results that we are generating. And these diamonds, if you look at the second diamond that is converging within the results we need, it's taking 4 minutes to run. So that's what this table says. So that is how we're verifying it, is by comparing it against these numerical methods that we had. I hope that clarifies both of the questions.
Thanks a lot, Yashika, for giving that beautiful overview and answering the question of Rachel. And so, guys, if you have any more questions for Yashika, please feel free. We will wait for maybe a couple of minutes more if you have some more questions. If not, then we would conclude today's webinar, the first episode of Webinar Wednesdays of SSSPG. Yes, Dia. So about the recording, we are recording the session and we will be posting it on the YouTube channel of SGSE. It would take a couple of weeks time to get it through. So expect it to be up on our YouTube channel next week or maybe the following week, but surely we would post the webinar there.
And I'm happy to connect with anyone later on as well. I know this is a pretty dry topic and a very technical, but I'm happy to answer questions later on as well. If anyone wants to connect on PhD life, academia, on how I got interested in this field, or what path you can take to do similar research in the future. And I'm sharing my email on the group chat as well in case anyone wants to chat later.
Thank you so much, Yashika. I'm sure everyone would love to connect to you, and once they have thought about it, they will ask you more questions. So thanks a lot, Yashika, for today's webinar. So Damien has one more question. Do you think that AI will enhance the calculation methods in the future?
Definitely. And I'm already seeing AI being incorporated in a lot of current industry tools. And I've actually experimented with it a bit, and it seems to get really, you have to give it a lot of guidance, which I think is happening in most fields. So you need to train the AI to learn the dynamical models that we wanted to use to understand the specific applications we need for it. But it's definitely a possibility in the future, or actually probably a definite in the future, that we'll see more AI incorporation in similar methods, and maybe the results will be even faster with the improvements that we see. And
Right,
there's a
absolutely. Thank
question,
you.
yeah.
Yes, Yashika. So there's one more question about possible collaborations, if any.
Yeah, I think most academia people are always open to, is this research? I'm assuming this is research collaboration, but most people in academia are very open to collaboration in research as well. So you can always feel free to send me an email at the email that I shared, and let me know what specific interests you have, and I can connect you with the right person or to chat with you as well.
Yeah, so Subramani, if you have any specific idea or question or topic to discuss, you can definitely send an email to Yashika and she will definitely go through the details and she will accordingly answer you. So Kirsty also asked, thank you for explaining such a complex area so simply. My background is not scientific and this was great. So that's a compliment from Kirsty for your amazing job today, Yashika. Thank you so much.
Thank you so much. I appreciate it, Kirsty.
All right, everyone. So I think that brings us to the end of today's webinar. Thank you once again, Yashika, for your time and for the brilliant presentation and also for all your answers. I'm sure each and every one of our audience today really enjoyed your webinar. So thank you so much for your time and effort, Yashika. Really appreciate it.
Thank you so much, Subhajit, for hosting.
And thank you so much to everyone for joining us today. This was the first episode of Webinar Wednesdays, and we will have many more episodes coming up. So on the first and the third Wednesdays of every month, we will be hosting someone who will, again, just like Yeshika, talk to us something about which they are passionate, and also we will learn so much from these webinars. So stay tuned and follow us on our social media channels, or stay in touch with us on our Slack. You will find every relevant information about the upcoming webinars in this particular series. And I will see you again very soon in the following Wednesday, that is January the 17th. So thank you so much, everyone, for joining today. It has been amazing. Bye-bye. See you again very, very soon. Take care, everyone.
Thanks, everyone. Bye.
Bye-bye.